right, everyone, thank you very much for joining this session on static analysis and search-based testing here at ISSTA. We're going to get started straight away with the first presentation on how effective smart contract analysis tools are. And the presentation is going to be given by Asim, who's with UBC. Please get going. Thank you.
Thank you for the introduction. My name is Asim, and I'll be giving a presentation on our paper on the security and testing of smart contracts. Smart contracts are basically small programs deployed on blockchain that are executed on every incoming transaction. And they interact with each other and with the regular blockchain accounts as well. There are actually several blockchain platforms that support running smart contracts, but in the current days, Ethereum is the most popular platform for running smart contracts. So we are targeting Ethereum contracts in our study. Ethereum smart contracts cannot be updated once deployed on the blockchain, and the transactions on these contracts are immutable. In addition to that, the financial nature of smart contracts provides a good incentive for attackers to target smart contracts, to find bugs and exploit them for financial gains. For example, the past few years witnessed several attack incidents that targeted smart contracts, and actually those attacks led to the loss of millions worth of Ether. So this actually highlights the need to do analysis of smart contracts to find bugs and fix them before deploying to the blockchain. There have been such tools proposed to discover security bugs in smart contracts, but we can see that code vulnerabilities are still reported frequently. So why these tools are not impacting the development of secure smart contract? Unfortunately, there is no such systematic approach or methodology that can be used to evaluate the efficacy of those proposed tools on detecting bugs. So our main goal in this study is to build a systematic approach for evaluating smart contract static analyzers. And the key area in our work is to inject bugs into all valid locations in the source code of smart contracts. We have proposed SolidiFl, which is a systematic and automatic approach for evaluating smart contract static analyzers. We applied our approach to evaluate 6 well-known static analyzers, and we did analysis of the false negatives and the false positives of those evaluated analyzers as well. We found that the evaluated tools failed actually to detect several bugs that they claim to detect, in addition to reporting high number of false positives. So as mentioned before, our approach is based on injecting bugs into the source code of smart contracts. And actually injecting bugs into smart contracts is a kind of a challenging problem. We are dealing with Solidity, which is different from traditional programming languages. And we inject bugs into all potential locations in the source code of smart contracts. At the same time, we want to inject bugs that can be activated by external attackers at runtime. So in our work, we formulate those bugs as code vulnerabilities or as code snippets that lead to vulnerabilities in the source code. We only inject bugs that the evaluated tools claim to detect. We play the role of developers, rather attackers, in introducing the bugs into the source code when developers actually do this carelessly. We try to inject bugs that are distinct as possible. For example, if we have these two snippets that have the same functionality. The first one use block timestamp directly to compare the equality, while the second one assign first the block timestamp to a variable and then use this variable in the if condition. Tools employing pattern matching, for example, will reason about these two snippets differently and may detect only the first one and skip the detection of the second one because they look for the use of block timestamp in specific patterns in the code. So these two snippets show how they have the same functionality, but tools will reason about them differently, so they are distinct bugs. So let's see how the bugs are actually injected in the contracts. Actually, our approach works on the AST level of the source code. I'll use this contract example to explain how our approach inject bugs. This contract can be used by a user as a personal wallet. So the constructor here will assign the address of the account that created this contract as the owner. And then the send to function will be used only by the owner to send money to other accounts. So the require statement here at line 14 checks if the one calling this function is the owner. And then the send statement here at line 15 performs the money transfer. So in our work, we use three different approaches to inject bugs into the source code of smart contracts. In the first approach, we do code transformation and change a piece of code to make it vulnerable to a specific bug. For example, if we have this statement that authenticates the contract owner, to inject a bug in this statement, for example, we just replace, for example, the global variable message changer with tx.origin to make this statement vulnerable to the use of tx.origin bug. In the second approach, we weaken the existing security mechanisms. For example, if we have this secure code that sends money and it checks the return value and reverts the fund or the function call if the send of the money failed. So we inject bug in this code by removing the current security mechanism. Here we comment the revert statement in this example. In the third approach, we inject full code snippets that are vulnerable to specific security bugs. For example, this example, here we inject this code that is vulnerable to reentrancy bug. So we used our approach to evaluate 6 well-known static analyzers. In our experiment, we used a data set of 50 smart contracts selected from Ether scans with different sizes and different functionalities. Those contracts were representative of Ether scan contracts. And in our study, we mainly aim to answer 3 main research questions. What are the false negatives and the false positives of the evaluated tools? And can the injected bugs be activated at runtime? So we injected bugs that are considered by most of the evaluated tools that belong to 7 common and different bug classes. We ended up by injecting about 9,400 distinct bugs. We granted each tool 15 minutes to do the analysis on each contract. So the table here shows the evaluated tools and the selected bug classes, and the star mention the bug classes that each tool is expected to detect. So let's discuss the result of our evaluation, and I'll start by the false negatives of the evaluated tools as presented in this table. In this table, we use NA to mention that the tool doesn't support detecting this type of bugs. And the check mark means that the tool was able to detect all the injected bugs. We present two numbers in each cell. Actually, we mean by false negatives here, either the bugs that the tool wasn't able to detect at all, and these are presented between the brackets, or the bugs where the tool wasn't able to correctly identify the type of the injected bugs. So the number on the top present both the undetected bugs plus misidentified bugs. From the result, we found that none of the tools was actually able to detect all the injected bugs. All the tools have several corner cases that are not able to detect, in addition to misidentifying a large number of bugs. Actually, those results were very surprising for us because we weren't trying to attack or break these tools. We were just trying to use the tools in the way they are expected to detect the bugs. So let's see this example that shows how tools misidentify bugs. In this example, we have this part of smart contract injected by reentrancy bug. We use Wenti analysis tool to scan this injected contract for bugs. Wenti reported that there is a bug of type transaction order dependency, rather reentrancy bug. So actually, misidentifying bugs can mislead developers and may result in leaving the bugs unfixed in the source code of contracts. In the second questions or research question, we evaluated the false positives of the evaluated tools. And we mean by false positives here, those bugs reported by the tools, but there were no bugs in reality. Unlike false negatives, where we know exactly where the bugs were injected in the source code, estimating or evaluating the false positives were challenging due to the lack of the ground truth, and so due to the large number of the reported bugs, which make manual inspections of those bugs expensive. So to address these challenges, we assume that all the bugs reported by the majority of the tools are true bugs. And then let's take this example that shows how our approach works. For example, if a tool reported 100 cases as reentrancy bugs, if 60 of these 100 were reported by the majority, so we'll exclude those 60 cases and we will consider them as true bugs. And then we will select 20 bugs out of the remaining 40 bugs and we will inspect them manually. If we found that, for example, 16 out of those 20 inspected manually are indeed false positive, we will estimate the number of false positives as the percentage of the bugs that we found indeed false positives multiplied by the number of the filtered bugs. There might be false positives that are actually reported by the majority of the tools, but in the worst case, we are underestimating the number of the false positives in this approach. From the result, we found that all the tools reported high false positive ranging from 2 to 800 cases. And the interesting thing is that the tools that reported low false negatives on some classes of bugs reported high number of false positives on these classes. For example, Slither was able to detect all the injected bugs of type reentrancy. At the same time, reported high number of cases as reentrancy bugs, and they were just false positives. In addition to that, some cases were truly bizarre. For example, this line of code that was reported as integer overflow, even though there is no integer variables or calculations in this line of code. Finally, we wanted to assess if the undetected bugs can be activated in the contracts at runtime. Actually, this will help us to understand if the tools didn't detect those bugs due to weaknesses in the tools or because the bugs are inactive. So to do this, we selected 5 samples from each class of bugs, and we deployed the contracts or the buggy contracts containing those bugs on Ethereum blockchain by connecting to Ethereum node called Infora. We have implemented a Python client to interact with those buggy contracts deployed on Ethereum. We were able to successfully interact with each bug in the deployed contracts on blockchain within just minutes. And this highlights how risky is not finding those bugs by the analysis tools. There are actually some threats to validity in our evaluations, and we try to mitigate them by selecting contracts that were representative of Etherscan contracts. In addition to that, we selected well-known bugs and common tools that are used in both academia and industry. We designed SolidiFl to be generic so that it can be extended easily to add other bug classes and evaluate other static tools. For more information on this, please reference our paper and our code available online. So to summarize, we have proposed SolidiFl for the purpose of evaluating smart contract static analysis tools. We found that static analyzers actually are still immature and suffer high false negatives and false positives. Actually, this is not just a problem in academia, as these static analyzers are used in industry as well. So this is a call from us to this community to invest in building better static analyzers that can be used to discover these bugs in smart contracts. Our work is available online and can be accessed using this link. Thank you, and I'm happy to answer your questions.
Thank you very much, Asim, for your presentation and obviously doing the work in the first instance. You've timed your presentation quite perfectly, so we got exactly the prescribed amount of time left for questions. And I'm quite happy to hand over the virtual microphone here to the audience for anyone who has questions to ask. Alternatively, you can obviously also follow up on the Slack channel and the like. Okay.
Okay. So how realistic are the seeded bugs, and to what extent do they cover the kinds of bugs? Yeah, actually, we during the selections of the set of bugs that we evaluated those tools on detecting them, we tried to select bugs that are common and that lead to vulnerabilities actually that have been exploited in reality. There have been several attacks in the wild that targeted vulnerabilities of this kind. So this mentioned that we try to select the bug or the set of bug classes that are common and realistic. And how realistic also? We tried also to follow the concept or the behavior of how these bugs are actually introduced or in the contracts, and to formulate the code snippets that are injected to the source code.
All right, brilliant. I hope that answers the question. So you get a thank you for that. Any further questions from anyone in the audience? I got something in the meantime while people are typing. So one thing which was certainly known in the early days of the SMT solvers is that every tool was good on its own set of benchmarks. Mm-hmm. Okay. Did you have a look which one of your subjects, or meaning your programs that you provide the tools for analysis, in a sense, have been used by the developers to debug and build and evaluate their tool? So to a degree, can anyone argue that you've used their benchmarks?
You mean by for the bugs for the tools?
Yeah. So did you check if the benchmarks or the problems you gave to the tools were known to the developers of the tools, or if these benchmarks are new, meaning haven't been given to these tools before?
In kind of the bugs, you mean? The benchmark of the injected bugs, you mean?
Yes. Yeah.
Yeah. So actually, yeah, as I mentioned before, those bug classes are not new. They are common, and they are well known for people in academia and in industry, and also most of the tools consider them. So which means that they are real bugs and considered, and the developers, they suffer from them. And most of these bugs are, there were real examples or real attacks that targeted them and exploited these vulnerabilities.
Just to be clear, so I was talking about the programs themselves. Obviously, the bug types were known before, but what about the actual programs?
The tools, you mean?
No, the programs, the actual programs that exhibit.
Okay, the data set for the contracts. Okay, there is a kind of container on which is renowned for that contains open source smart contracts. It's well known in the community and for smart contracts developers.
So you're assuming everyone has seen all the bugs, even if
yeah. So we try to select them randomly from Etherscans, so that they can so that they can be representative, different sizes. They contain different syntactic features and different functionalities.
Okay, brilliant. Thank you very much. If I would please ask the second speaker to get ready and share their slides. So the next presentation is going to be on a programming model for semi-implicit parallelization of static analyses. And it's going to be given by Dominik, who's with Technical University of Darmstadt in Germany.
Yeah, thank you. So as introduced, I'm Dominik, and I'm presenting a programming model for semi-implicit parallelization of static analyses, which is joint work with Florian Kübler, Jan Thomas Kölzer, Philipp Haller, Michael Eichberg, Guido Salvaneschi, and Mira Mezzini from Technical University of Darmstadt and KTH Royal Institute of Technology. Before going into the details of what the paper is about, I have to do a little bit of history so you get where we're coming from. So 3 of my co-authors, together with Simon Geris in 2016, proposed reactive async, a novel programming model for concurrency that is a generalization of futures and promises in such a way that you can have multiple updates of one value instead of only a single completion. And it also handles cyclic computations. So how is this structured? Reactive async is based on cells that are like futures, but can be updated several times. So here's just some Scala example code that creates 2 cells and initializes them with a value of pure for what could be a simple purity analysis. And we visualize these cells as some entities that have this value currently. So these cells, they can have dependencies that are created by giving a callback function that will be invoked when the dependee cell is updated. So this is simple callback that will update cell 2 when there's an update of cell 1, and it just checks whether the new value of cell 1 is impure, then it will also turn cell 2 to impure. Otherwise, this callback returns no outcome, which means that cell 2 stays at the value it currently has. And we visualize this dependency that is now created by that arrow between the cells. We can then use a cell completer to update a cell, and the code shown here will get the cell completer for cell 1 and put a value of impure in there. We use put final to put a single value there, but there's also a put next method that you could use to not finalize the cell, but keep it open to do further updates later on. The cell is updated and we highlight it. And because of the update, that continuation, that callback that we have registered on cell 2 is triggered, which causes that cell to update itself according to the callback, which said if the first cell was impure, the cell shall be impure too. So because that was a final update on the first cell, this does remove the dependency because there cannot be any update anymore. Now, one important thing to note is that when you put a new value into a cell, this does not set the cell's value directly, but instead each cell is associated with a lattice, and we invoke the join operator of that lattice with a new value that is supplied to the put final or put next function, and we combine it with the old value of the cell that was stored there before. And this allows these dependencies to be executed concurrently because the join function is guaranteed to produce the same lattice value regardless of the order in which these updates are processed. Now, as I said in the beginning, reactive async can handle cyclic dependencies. It does this by finding out where the state of the system is quiescence, that is, there are no more updates to be processed. And once the state is reached, it identifies all cycles that are there, and the user-supplied function resolves these cycles, typically like the one shown here. This is pretty simple and will just map a cell to some specific value or to its current value. There's also a possibility that cells are not yet completed but do not have any dependencies left. Then there's a second similar function that can finalize a single cell. Now, this reactive async provides some important features that can be used for static analyses, because typically static analyses deal with lattice-based data, so that's a good fit. They tend to have many dependencies, and that kind of automatic dependency management of reactive async is helpful with this. And of course, the dependencies in static analysis are often cyclic, so we do need that resolution that is not given by other forms of concurrency primitives. However, for more complex real-world analyses, what reactive async provides is not yet suitable. There's some expressivity missing to implement complexer analyses, and also the performance for analyzing large programs is not on par with the typical static analysis frameworks. So this is the point where we started to build on top of that, what we now call reactive async 2, to provide a framework for easy parallelization of more complex static analyses. And there's 4 major contributions that we have in reactive async 2 that build on top of reactive async to do so. And the first one is to address the expressivity issue by introducing sequential cells that allow analyses to store mutable state between invocations of the continuation functions of the callbacks. The other 3 are more important for performance reasons, because those joint functions on lattices can be pretty costly, and in some cases they can be avoided. And therefore, we give users the option to provide custom functions, how cells shall be updated to avoid these additional costs. We can aggregate updates to have less updates to be propagated, which also greatly can increase performance. And finally, the order in which updates are processed is also pretty important for performance. So we let users supply scheduling strategies that define how the updates shall be ordered. And I will discuss all of these 4 in detail now. So sequential cells are necessary for mutable state, because when you have several continuations running concurrently that target the same cell, and this cell has some mutable state aside from the cell's value itself, this is going to be trouble. But we can now create sequential cells, and when we have several dependencies for them, those continuations that target the same cell, in this case sex cell 1, those will not be executed concurrently ever, but they will be only executed sequentially. However, we can still execute continuations for other cells at the same time, so we don't really use concurrency usually, because the number of cells typically is very large, and so there's always some other cell for which some continuation can be executed. So mutable cell state is important, for example, if you want some more manual dependency management, so the continuation function can know when there's no longer any dependencies, or if you have some more complex state that you have to deal with. Secondly, as I already said, there's custom updaters that allow you to give different semantics on put calls as put next, put final calls on the cell completers, instead of just using the default semantics of joining according to the lattice given. This is because in some cases, analyses already have to perform that join operation, for example, on their internal state. And so we can combine this with sequential cells to just provide an updater that restores kind of the simple semantics of not performing a join, but just putting the value over. There may be potential for more complex updaters, but mostly for performance reasons, we use that simple one that just sets the value, because with sequential cells, we know we're the only continuation that is currently executing. We can modify the mutable state, and we can perform the join operation if we have to do so in the analysis anyway, just once and not twice. Now, the third major contribution is aggregation of updates, because cell updates are propagated, but the continuations are not executed immediately. They are put into work queue from which worker threads will execute these continuations once there's time available to execute them. But until one continuation is executed, the cell that triggered this execution may have already been updated again. So there's no use in processing the intermediate value, but we can just process the new value that is already available. On the other hand, the target cell of the update may have other dependencies, and they may also have gotten updates. And so instead of just processing an update from one source cell, we can process a list of updates of several cells, and this may reduce the number of updates that are triggered further down the line, because the target cell is only updated once instead of several times. Yeah, so as I said, we can aggregate all of these updates both to the original source cell that triggered the update and from other source cells on which the target cell also depends. So we have to execute the continuation just once, and that can significantly reduce the number of updates to be propagated. Finally, the processing order of updates may impact the performance. And there are two factors that kind of work in different directions. One is if you have some important updates, like, for example, final updates, you may get faster conversion if you propagate them early on instead of having them sit at the back of some work list. On the other hand, if you can delay some update, then until that update is executed, there's more opportunity for more updates to the same cell to arrive that can be aggregated, and therefore reduce the number of updates that have to be propagated down the line. So because there are two competing factors, this actual impact of both of these may depend on the concrete analysis you're running or on the target program. And therefore, instead of just selecting one size fits all strategy, we let the analysis developer decide on the correct strategy to be used. So we supply 8 basic strategies that are derived from 4 similar patterns that just analyze the local structure of the dependency graph. And those are shown here graphically. The first one on the upper left shows a target cell of an update that has many source cells. And that, for example, may mean if such an update, as shown here in red, is delayed, there's lots of potential for more aggregation on the target cell. On the upper right, you see kind of the turned around for a source cell that has many target cells that need to be updated because the source cell currently has got an update. Then on the lower row, you have similar strategies where the target cell has many target cells down the line, or where the source cell has many cells on which it depends. So we performed some extensive evaluation by implementing an IFDS solver and a simple analysis on this. And we evaluated both the strategies that I just showed, and we compared against other solvers. So what you can see in this figure is actually quite a lot. So most of these lines are different scheduling strategies that I just showed. This is only half of them. This are the ones that delay updates that may have a larger influence, because the other strategies turned out to perform significantly worse than what is shown here and would not have fit the figure. You can also see a flat line at around 60 seconds of runtime, where we ran essentially the same analysis on essentially the same IFDS solver, but implemented in the Opal framework with a sequential solver. And you can see that our strategies can beat this at around 2 to 4 threads easily. The last comparison that we have here is to the state-of-the-art IFDS solver Heros, that is also framework independent, and we used it on top of Opal, just as we used reactive async on top of Opal to provide a level baseline. And as you can see, Heros shows a similar behavior in speed up for up to about 8 threads, but then performance on Heros decreases again, while on reactive async, we still get benefits, even if diminishing for 10, 16, or 20 threads. So this evaluation was performed on a machine with, I think, 16 virtual threads. So it is expected to not perform much better with more threads, but we do not have the slowdown that Heros shows. So for final recap, what I presented was reactive async, reactive async 2, which builds on the original reactive async to create a framework for more complex static analyses by introducing first sequential cells that allow for mutable state, second, custom updaters that can be used to avoid the cost of additional joins if they are not needed, third, aggregating updates to reduce the number of updates that need to be propagated, and fourth, custom scheduling strategies that also have a big impact on performance. And all of our code is available under BSD2 clause license at the URL given here. So thank you for listening, and I'm open for your questions.
So let me first take the opportunity to thank you for your presentation and having done all the work and submitting to ISSTA. So next I should perhaps echo the apologies from the ISSTA team about the issues with the screen share and the flicker that some of you are seeing. So certainly I'm seeing it as well, and it is obviously rather unpleasant. This shouldn't disturb us, it shouldn't stop us from asking questions around this presentation. Let me just see if you have any in the chat. Not quite yet, so I will inject a question of my own. So one of the things you've shown is that sort of your return you had from adding more threads was starting to lose a bit of oomph, something like 4 threads, maybe 5 threads onwards. Is that fair to say?
Yeah, so we did run the experiment for 2, 4, 8, 10, 16, 20 threads.
Do you want to speculate on the cause of this? So very often one thing that happens when people try to parallelize algorithms on a single machine is that they quite simply reach the limit of the bandwidth that the CPU has to main memory. Do you believe that this could be the cause here? Or is
this could certainly be the cause, because these analyses tend to be pretty memory intensive. So I would also suggest that we might have some communication overhead, of course, for the parallelization that may also contribute to the slowdown. but I think, yes, main memory bandwidth might be a problem too.
All right, so we have reached the end of the allocated slot, so let me thank you again for your presentation. And if the next speaker would please get ready for the screen share, we're hoping it will have no flicker in it. For the final paper in the session, which is going to be on recovering fitness gradients for interprocedural Boolean flags in SBT. The presentation is going to be given by Yun Lin, who is with NUS in Singapore. Please.
Okay, I'm going to start now. Thanks for Daniel's introductions. And hi, everyone. I'm Yun Lin from National University of Singapore. In this talk, I'm going to introduce our gradient recovery work on search-based testing. It is joint work of National University of Singapore, Singapore Management University, University of Hangzhou, and Xi'an Jiao Tong University. Search-based software testing, or SBST, regards software testing research as an optimization problem, which requires defining an optimization goal, evaluating the fitness of the solutions, and mutating the solutions for approaching the goal. Similarly, SBST has an optimization goal of generating tests to cover a tiled branch in the program, a measurement to evaluate how far a generated test is away from covering the branch, and a set of mutations to derive a new test closer to cover the tiled branch. And here is examples, where the optimization goal is to generate tests to cover the condition in red. That is, we aim to generate a test to excite the branch condition where the absolute value of x is equal to 123. A random testing might generate a test like a equal to 0, b is 0, and SBST approach will usually using a measurement called branch distance to evaluate how far a given test is away from covering the branch. In this example, the branch distance is defined as the absolute value of the difference between two operands in this condition. Thus, the branch distance is calculated as the absolute value of the difference of 0 and 123, that is 123. The less the branch distance, the closer a test is to cover the tiled branch. More details of the tiled branch can be referred in this paper. Based on the branch distance, we can see that a better solutions can be a equals 0 and b equals 100. It is because its branch distance becomes 23 now, which is smaller than 123. Keeping mutating this test, SBST allows us to finally find a test whose branch distance is 0. Once a 0 branch distance is achieved, we then have a test covering the tiled branch. In this process, the measurement of the branch distance provides a gradient, allowing us to gradually change from the solution of 0, 0 to the solution of 23, 100. SBST has proved it's practical in many scenarios. However, if we would like to use the same approach to cover this condition, the measurement of the branch distance can no longer work. When we calculate the branch distance of the red condition, which checks the Boolean return value of a method call, the branch distance becomes either 0 or 1, as the operands of these conditions is either true or false. Without gradient, search-based testing degrades to the random testing, and we can only satisfy the conditions by luck. Given condition, if one of the operands depends on the return value of a method call with Boolean return value, we say that an interprocedural flag problem happens. When interprocedural flag problem happens, SBST usually degrades to random testing. And the rationale of our solution is simple. Once we detect an interprocedural flag problem, we further investigate the invoked flag method and identify the branch inside, which can return the required flag. If this branch distance has gradient, we use this branch distance to replace the branch distance of the flag condition. Thus, a gradient can be recovered. In practice, we usually normalize the branch distance between 0 and 1. However, there are 3 challenges to recover the gradients for the interprocedural flag problems. The first is the multipass problems. The invoked flag method can have many branches to return the required flag. Each branch has its own branch distance, and how can we choose them? The second is cascade interprocedural flag problems. there can be another interprocedural flat problems in the invoked flat method. We need to handle the cascading interprocedural flat problems in practice. And the third is the call and iteration context problems. If a flat problem is called in the loop or called in many call sites, the branch for the required flat can have multiple branch distance. Each iteration or call site can derive a new branch distance. Here is an example. Giving the input of array keys equals 0, 1, the loop has 2 iterations. In each iteration, the method check value is executed in a different way. In the first iteration, the executions go through the first and the third condition for the required flat. And in the second condition, in the second iterations, the executions go through the first and the second conditions for the required flat. Different executions lead to different branch distance to reach the required flat. Therefore, which branch distance should we use in such a case? Note that the above problems can cohappen for an individual method suffering from the interprocedural flat problems. In this work, we propose the graph working aggregation algorithms to address the challenges of multipath problems and the cascade interprocedural flat problems. Moreover, we calculate context-sensitive branch distance to address the challenges of call and iteration context problems. When an interprocedural problem happens, the invoked method is called the flat method, and each flat method can have a few required flags. As long as those return instructions is excised, the interprocedural flag can be satisfied. Moreover, we call the branch guarding the required flag as the required flag. And we also record the trace of the executed branch towards the required flag. And as a result, each branch distance will have call context and iteration context. In this example, it indicates that the branch distance of 1.99 happens under the call context of the example and the check value method. Here, the method check value is called in the call site of line 2 in the method example. So by tracking the call and iteration context, we can distinguish different branch distance for the same required branch. Then we can aggregate those branch distance to cover gradients later. Based on the collected contextual branch distance, we developed a graph working algorithm to aggregate the branch distance of each required flat. The idea is that when we detect interprocedural flat problems, we statically work through the cascaded call graphs and their control flow graph in each call to find all the required flags and aggregate their branch distance back to the interprocedural flag. Here is an example. The target method calls a flag method check value, and the method check value for the call method is special. The first step is to identify all the required branches in the flag method. Then we assign the contextual branch distance for each required branch. Note that the required branch can have multiple contexts, thus they have multiple branch distance. Next, we aggregate multiple branch distance into one branch distance. I will explain more about aggregation details later. And however, some required flags will further involve a new interprocedural flag problems. In this case, we recursively identify their required flags and investigate the contextual branch distance of their corresponding required branches. Note that in this process, we work through the call graph and the control flow graph of each method call. When finding a new interprocedural flag problem happens, we will work into the control flow graph of the flag method. Thus, we can also record its call site before working into the control flow graph. When checking a required branch, we now already have the working path from the title method to its flag method. We only use the branch distance with the context aligning with the working path. In this example, the method example should call method check value at the call site of line 2, and the method check value should call the method is special at line 5. We only use the branch distance with such a call context. After investigating all the contextual branch distance, we will further aggregate the branch distance from multiple paths. In this example, we will aggregate the branch distance from line 1 and line 2 in the method is special. Then we propagated the aggregated distance back to the initial interprocedural method. By this means, the original Boolean value, the Boolean flag, will be replaced with a continuous value with gradients, allowing us to facilitate SBST in an effective way. Here is a few tips of our graph working aggregation algorithms. The first tip is that without distinguishing contextual branch distance for different core size iterations, the aggregation process can confuse some uncoupled branch as a coupled branch. As a result, the aggregated branch distance becomes misleading. And the second tip is that our aggregation from multiple passes or multiple branch contexts need to satisfy the following properties. First, when we are aggregating multiple branch distance, if one branch distance is close to 0, the overall aggregated value should also approach 0. And second, the aggregated distance should be more sensitive to the smaller distance. In general, the smaller the distance, the more promising its corresponding required branch. Therefore, we should give priority to those required branches. Mathematically, the derivative of the aggregation function towards the distance, vi, should be antimonotonic to vi. Given the limitation of the presentation time, interest audience can refer to a paper for more justification details. We implement our approach on top of EVA-Swade framework, which is a very famous SBST framework. We named our tool as EVA-If. It is actually for EVA-Swade for interprocedural flag. In our experiment, we compare our approach with EVA-Swade as a baseline. We select 807 Java methods from 150 open source projects. From those projects, there are 9.3K methods suffering from interprocedural flag problems. In this experiment, we removed some biased methods. For example, some interprocedural flag methods cannot be instrumented. And some methods like .equals method in JDK library, which cannot be instrumented. We also removed some title methods with very complicated objects. The reason is that EVA-Swade cannot construct the test case to create such objects. So both EVA-Swade and EVA-If achieve zero coverage. The reason is that it cannot construct the legitimate objects, so it will keep reporting runtime exception. Therefore, we remove all these kind of the noise methods for more meaningful evaluation and comparison. After removing those methods, we will have 807 methods left for the experiment. And we run each method with EVA-Swade and EVA-If for 100 seconds and for 10 times. And here is our experiment results. We first observed that on 11.8% of methods in all the projects are suffer from interprocedural flag problems. It means that such a problem is very prevalent and influential, and very influential to the effects of SBST. And second, we can see that EVA-If outperform EVA-Swade in methods with interprocedural flags. We actually divide the methods in the experiment into the following 5 scenarios, where first EVA-If will have better coverage than EVA-Swade, and second, EVA-If have equal coverage with EVA-Swade but use less time budget, and third, EVA-If has equal coverage with EVA-Swade and use the same time budget, and fourth, EVA-If has equal coverage with EVA-Swade but use more time budget, and last, EVA-If will have worse coverage with EVA-Swade. You can see that EVA-If improved the coverage in a large number of methods. Moreover, the overall advantage is statistically significant. And we also observe that EVA-If may incur more runtime overhead. The reason is that it requires more instrumentation to record the contextual sensitive branch distance. We also look into the method where the EVA-If does not improve EVA-Swade. The major reason lies in two folds. The first is that some interprocedural flag is trivial, which means that it can be covered by random testing. Thus, even if and it has the same performance with even if we have the same performance with either suite. And the second is that the larger runtime overhead sometimes impair the runtime performance of either if. Here is an example. The interprocedural flag is guarded by a normal branch. In the normal branch, if has an advantage to search to equal string, as it will spend less time to generate the individual test because it does not require a lot of instrumentation. Thus, it can find a solution faster. In this example, even if haven't covered the first branch within the time budget, thus either suite will outperform even if. However, we also observe that even if can outperform either suite as long as we give longer time budget up to 200 seconds. Now here comes the takeaway for my talk. In this work, we introduce a gradient recovery approach to address interprocedural flag problems in SBST. We developed two techniques to this end. We have context-sensitive branch distance to address the core and iteration context problems, and we have graph working algorithm to address the multiple path problems and cascading interprocedural flag problems. Based on the experiment, we show the effectiveness of approach, and our observation on the experimental results show that our approach requires more instrumentation for recovering the gradient, which can be regarded as a strategy to trade the time overhead for more gradient information for test efficiency. A more promising improvement of work is to understand when if can outperform either suite and vice versa. Thus, we can pursue a hybrid approach, keeping both low runtime overhead while still having the necessary gradient information to improve the test efficiency. Okay, that is all my talk, and I'm happy to have your questions.
All right, we'll give everyone a second to digest this. So let me use some of the time to thank the speaker for the excellent presentation. Thank you very much. So we'll give you a warm-up question while people are contemplating theirs. So you're mentioning on your key takeaway slide, one of your contributions, which is the idea of using a branch distance in this calculation to produce a gradient. And the reason you've given is that this prevents the confusion of different branches, which means that different branches would have different relative weights when you make changes to inputs. I mean, this is a problem which also exists in a non-interprocedural setting, meaning even if there's just one procedure, when you can have similar issues. So I see this as somewhat orthogonal to the question of interprocedural analyses in general, or specifically the interprocedural flag problem. So one answer which has been given to this is to use a vector of gradients as opposed to just a single gradient. Did you try that?
Actually, we tried it anyway. So when we have a vector of the gradients, so we supposed to have multiple gradients. So here comes the problem of when we have multiple gradients, and which gradient should we take? Of course, we can have some technical solution that we support multiple gradients and let multiple gradients involved by its own. But anyway, we haven't tried that solutions, but that is still a possible solutions. And our solution is that we aggregate all these gradients. So as long as one gradient will take effect, and the effect will be enlarged and augmented, so that the overall evolutions will just work in such a good directions. And one of my comments is that yes, it is definitely an orthogonal problem that the normal SBST will still have a multiple gradients problems and the confusion problems. But when we have aggregation, because we need to aggregate multiple gradients there, so as long as there are confusions, our gradients were significantly screwed. So one idea is that suppose one branch distance, so once the branch distance, if a branch distance is 0, so it means that this branch has been covered. So when we do the aggregations, as long as one branch is covered, after we do the gradients, we will believe that and this branch is definitely covered. Because when we do aggregations, as long as one of the branch make a confusion, and the whole result of the aggregated result will be get confused. So the problem will be more severe in our settings. So we have to address these problems instead of just letting go.
Okay, thank you very much. We are exactly at the end of the session. And I would like to use the opportunity to thank all speakers, all the 3 speakers who gave representation in this session. And I would like to invite you to join us in the mini break session on Zoom for the next 20 minutes, after which we'll start the next session. Thank you very much.
Thank you.